someone would be so kind, any of you who have had difficulties with getting to the recordings, please please go ahead and send me a in the meeting chat, send me a message. If you have not, don't. Okay. Favorite beverages in hand, everyone?
Yep.
Okay, good. So this is your data from the cratered highlands, and what I did was I made it a what is it called? Bar chart, so that you can actually see the smaller craters are more dominant. N is the number of craters that I found, and crater size is in kilometers. And so you can see that that there's not a lot of craters that are very large. It's mostly smaller stuff, and it kind of skews to the left if you were to think about it from an average. And you could probably, if you were ambitious, and even if you're, well, yeah, if you're ambitious, just take all the craters and do what is called a weighted average. So you would actually say, let's see, the total number. I know you guys love statistics, so I'll get you into it. +4 +4 +4 +3 +2 +1 +3 +3. Now this is my numbers, so by all means use yours on your lab. There are 61 craters all told, at least from what I saw. Now I could be wrong. It's a subjective. It's a bit of a subjective thing, and I could miss something due to the detail of the picture. But what I got was 61. So N is equal to 61 craters. And what you would do for a weighted average is calculate the percentage of each one that you got. So 19, I got 19 craters that were 0.2 and below, divided by 61. That gives me 31%. So I'd multiply 0.31 times 16 plus 18 divided by 61. 29, 0.29 divided 0.29 times 18, and then just do a weighted average, and then you could find the average crater size. Oh, I'm sorry, I'm saying this wrong. So 0.31 times 16 kilometers plus 29% times or 0.29 times 32, and so on. You would calculate the percentage for each one, and then you could calculate a weighted average of the actual average crater size in the cratered highlands. You could also do the same for the upper mare region. And as a matter of fact, let me pull that up. This is what I got for the upper mare region. Let me just show you that. Highest number I got was 5, and they were small. So again, you could do a weighted average to figure out the crater size for all of those. And again, the problem with that, with any picture that you get of a planetary surface, is its resolution. And one of the things that this lab taught you, and you're going to see again in another lab fairly soon, is scale factors and how to figure out the actual size of these things based on your picture and based on the scale of the picture. We do this all the time. If I were a planetary scientist, that's what I would be doing a lot. And so, what I hope that you didn't find this lab too frustrating, but I also hope you understand that you're actually doing astronomy, not just reading about it, but doing it. So, any questions on that lab? No, we're okay.
I believe so, yes.
Okay. I know Abigail was actually chatting with me on a few occasions this weekend, and that's fine. As a matter of fact, I applaud that. Okay, so what I'd like to do is get into this little business on connecting interiors and planetary surfaces. The interior you probably read a little bit about over the weekend, at least I hope you did. The next lab, by the way, we will do is on climate, and that should be, let me check the teams, because I'm pretty sure I uploaded it. Planetary climates. And this actually had 2 labs associated with it. You're only doing one, activity 13. You're not doing the second one on calculating storm size. Although it would be an interesting lab, and I did think about assigning it. I also thought that you have enough to be getting on with between your other classes and me that I don't need to drown you. And I've been trying not to. I don't know if I've succeeded, but I've tried. Let's see. So, again, chat me or send a chat if you are unable to get to the recordings. To me, this whole business of recording is very important, and I'd like to make sure that people are able to get to this. Now, I'm going to put a slideshow up, and I'm going to put it in the lecture notes section so that it doesn't drown us, because it's a fair-sized presentation, and I was integrating a couple of things in. I found some additional resources that I'd like to share with you, and I'm going to try my best again not to overload you. And at the same time, I'd like to give you, as they say, your money's worth in terms of this stuff. And once again, the idea is a couple of things. Number one, I want you to see why we say what we say. And I also would like to dispel the mythologies that are starting to become all too prevalent in our society, and I'm not sure where this is coming from. I really don't understand. I have a genuine lack of ability to understand the conspiracy theories. That makes any sense to you? And that's what I see coming up all over the place. Even with this COVID situation that we have, there are people who are saying, oh, it's a conspiracy by the government because it was the actual 5G towers that caused the coronavirus, and things like that. Basic hypothesis to lay blame on something else. And because people don't know, they actually fall prey to this kind of stuff. So to me, my mission becomes even more important in that regards, is to give you the critical thinking skills. You hear something, like I say, the moon is made of regolith. I don't want you to accept it. I absolutely do not want you to accept that. I want you to say, how in the hell do you know that? Because that's really what this is all about. You guys are not going to be scientists, and I get that. unless some of you decide I corrupt some of you, which I would certainly try to. But seriously, going back to my point, you guys are going to be citizens, and you guys need to be able to make good decisions, whether it's on should I fund this rocket to Venus, or should I take this medication? Why should I take this? Should I take this medication? What's it going to do to me? What's the side effects going to do to me? So I'm trying to kill many birds with the one single stone, and I can't say that's easy, but we'll do our best. Okay, so there's what is called AST 101, terrestrial, Mercury, Mars, and the Moon, PPTX, going into the lecture notes section of our class. I'm sorry to say it is gigantic. It's 500 meg, because of course there are movies all over the place. So it may take a little bit to download depending upon your connection, but hopefully you will find it useful. There will be a Quizlet posted by no later than Tuesday morning on this stuff, so be aware of that. Make sure you study. And are there any questions before I begin? We're happy? Somewhat happy?
Happy as we can be, Ubin.
Okay, fair enough, Tricia. Okay, so let me see if I can't pull up some stuff. And there's one other thing I need to pull up, or try to, and it's not here. Let me pull this up. I have so many shortcuts that it's becoming almost impossible to find anything, even with the shortcuts. You know the drill on this. Okay, so there's M in chapter 10. Okay, so I don't want to share this particular one just yet, but I do want to do this. So before I get into the planets themselves, I'd like to show you a couple things. I did not change this thing. I'm sorry. The connecting planetary surfaces and interiors. So, Tricia, you are on Alien. Oh, wait, where am I sharing? Hang on. Okay, you are an alien on a spaceship, and you're coming into the solar system. And you see there are some rocky bodies ahead, between 0.38 and 1.5 AU from the sun. You fly by each and every one of these bodies, and my question to you would be, what do you notice about those bodies? And go superficial. It's okay. What's the first thing you're going to notice?
The color, probably.
Color, good. Okay. The color of what?
The surface of the planet.
Good. So you're going to notice the color. And let's say, Tricia, for sake of argument, you are bionic woman, which, being a parent, you almost have to be anyway.
Right.
Yeah. And you are able to see via radar waves. So when you look at Mercury, you'll see Mercury playing, like what you see on the left-hand image here. And then you see Venus, and you get rid of all the clouds because you are bionic girl. And you see what Venus looks like without clouds, and Earth, and then the Moon, and then Mars. So the next thing you're going to notice the color of the surface. What else are you going to notice? And if somebody else wants to shout out, by all means, shout out.
Even the temperature?
Can you notice the temperature? You have infrared?
The craters.
Yes, yes. You're going to notice well, you can notice the temperature. You may notice the temperature. Maybe you can get a sensor reading. So I didn't mean, I hope that that wasn't taken the wrong way. I'm just saying, you know, with your eyes on a superficial basis, you'll notice the color. You'll also notice the craters or the lack thereof. True?
The size.
Say again.
The size of the planets.
Size of the planets. Good. Yes. Absolutely right. So another comment is that, you know, why is the moon so small? Why is Mars so small and Mercury so small and Venus and Earth so large? So that's another thing you'll notice. You'll notice the color. You'll notice that Venus, and this is an artificial color, but we'll take it, is kind of orangish yellow. Would you agree?
Yeah.
Yeah. Whereas Mercury and the Earth's moon, after you do the flyby and you review the tapes, you see they're kind of gray. And Mars is kind of reddish. And the only planet that really is nicely colored is the Earth. I'm very partial to blue. So maybe that's a little bias on my part. So the key idea here today, before I go into the planets themselves, is what's going on in the interior. And you, Trisha, bionic woman though you are, can't see that. You can't see what's going on in the interior, but you can infer. Okay? So here's the deal. On the planet Zarquan, where you come from, Trisha, you have things like earthquakes, right? And you have volcanoes. And there are different types of volcanoes on your planet. There are these super tall volcanoes that, you know, you as a child witnessed one coming up, and it was, let's see, how do I want to phrase this? It had very thick lava, and it came up and grew to a great height, almost like 15,000 feet, kind of like a 14er here. And, you know, on Zarquan, that kind of volcano is called a stratovolcano. It's a stratovolcano because of the fact that it is so tall. Then you had another type of volcano come up, and this volcano had somewhat runny lava, you know, not super thick or anything like that, but it had very runny lava. And you decided, because it looked like a shield, that you would call it a shield volcano. And then you have one other one, and I'm trying to come up with the name for it, but it more or less is like a flat little dome. And it reminds you of your absolutely favorite breakfast food on Zarquan called a pancake. So you call it a pancake volcano. So those are the types of volcanoes that you have on Zarquan. You also have quakes. Now, here's the deal with the quake, and I'm going to share my camera for just a second, if I can. And, oh yeah, I'm here. So you have two types of quakes. Okay, on Zarquan, you have a quake that goes like this. And you notice what that does is it actually crushes the rock. So you're going to call this, it crushes the rock pressure. So you're going to call this a P-class earthquake, tectonic activity. Then you have another one, and you got stuck in this at one point in time. You were in the first city of Zarquan, and that has a fault running through it. So you have another type of quake that you were sitting in that does this. So this is called a shear, or because it shears the side of the fault. So we're going to call it a shearing earthquake. Okay, so Zarquan is very, very active. Okay. Okay, so let me go back for a second. And I hear my monsters here. Let's see, I'm opening the wrong thing. Good. Nice. Let me get out of that. Stop sharing that. There we go. That's the one I wanted to share. Can everybody see the terrestrial planets? What's the terrestrial planets like on the inside?
Yeah.
Not Russia planets, but terrestrial planets. Okay. Okay, so here's one. Yeah, I know. The captions are rather amusing. So you come from Zarquan, and you see these 4 planets. You notice there's a lot of craters on 2 of them, but not so many on these other 2. And then a mix on the last one. So let's talk about what you can infer. Number 1, maybe. There we go. Okay. Seismic waves. Now, seismic waves on Zarquan will probably be the same on these planets. So you can say, oh, look, there's some kind of crack somewhere. There must be some kind of S or P wave coming through that's making things crack. But here you have vibrations that travel through the Earth's through the planet's interior, and Zarquan. So you have a S wave and you have P waves, but here's the thing. This body here is composed of a solid inner core, a liquid outer core, a mantle, and what is called a lithosphere. And I kind of mixed up the order of the slides, so I apologize on that. But here's the deal. With a seismic wave, like an earthquake, it can travel from this point to this point through the liquid, hit the solid, be reflected off the solid, and then hit another solid, and then be reflected, etc., etc. But if it hits another media, say like a liquid, the P wave can actually go through, but it's bent. Okay, it's as if you're going from air to glass. And so here's my air. It's going through the mantle, but now we have another type of wave, the S wave, which actually gets stopped by the liquid. So it literally will bounce off and become what is called a standing wave. So it'll keep bouncing back and forth until it dissipates. So seismic waves would be one thing we could possibly see. And we by seeing these faults, we can infer that something is happening on the surface. So I blew it with the order, and I apologize. But let's take a look at Zarquan's interior. So the structure of Zarquan, and for that matter, any terrestrial planet, is shown here. Now you kind of read that in the guides that I sent you, but I want to attack it again from another point of view. I'm sorry, I need to interrupt for just a minute, and I'll be right back. I really apologize. Let's see. All right, I apologize. She's usually not that loud. Everybody okay so far?
Yes.
Yep.
Okay. We survived the arrival of our little Alunia Petunia. Okay, so let me get back to the point. Here is Earth's interior, and this is true of any terrestrial planet. High density core, typically of nickel and iron. And I remind you, if you're not sure why that is, just remember the ice cream example. Trisha, you need to stop leaving the ice cream out. I really missed my ice cream. Sorry, couldn't resist. Couldn't resist. And then you have you have an inner and outer core. Then you have a mantle, which is moderate density, based in silicon, oxygen, etc. And then you have the crust, which is the lowest density, basically made of granite and basalt. Okay, so it's like I was saying, the chocolate chips fall to the bottom of the container. There's a little bit of cream in the middle, and then a lot of the lighter, fluffy stuff at the top. So the upshot is that all terrestrial planets have the same structure. Now, the weird side of this is the fact of Mercury. Mercury, the radius, the diameter of Mercury is 75% core, iron nickel. And no one understands why that is. Okay, it's very, very odd. But all of these planets, all of them have this iron core, the mantle, which is semi-molten, and the lithosphere and the crust, which is basically rocky, lightest stuff out there. A few more words on this. If you are very fortunate, your core is either liquid or semi-liquid. You are in trouble if it is not. And there's reasons for that, and we'll talk about that in just a moment. For example, we have strong evidence that Mars has a tiny bit of liquid left, but it is mostly solid. And the same will be true for Mercury and the Moon. And these are the guys I'm going to cover today when we get out of this. But this PowerPoint should be available to you guys ultimately. And in the meantime, I'm filming this as well. So you should be able to have this as a reference. So all terrestrial planets, Zarquan, Earth, Venus, Mars, Mercury, Moon, all follow this pattern. And we've inferred the interior Mercury to be as it is because there's a moderate sized, well, there's evidence for that, and I'll talk about it. Let me just not get distracted. However, all of these bodies have that same structure, okay? And we're going to assume that S and P waves behave there too the same way that they do here on Earth. It may be that the thickness is a little bit different, but other than that. Okay, so the reason the core is as heavy as it is differentiation. So gravity, in essence, is pulling the high density material to the center, and lower density material rises to the surface. So when you look at the layers, and this is the key point I want you to take away from this slide, it all varies on density. The lowest density material is going to be the rocky crust. The medium density material is going to be the mantle, and the metal core is going to be the highest density. So There's one other place that I didn't really describe here, and that's called the rigid lithosphere. And it is the barrier between the crust and the mantle. Okay, and so it essentially, depending upon the planet, floats on the warmer, softer mantle below, but it is hard and rigid. So here's the thing. Do all planets have tectonic plates? The answer is no. Venus and Mars, and for that matter, Mercury, do not have tectonic plates. They are one crust. Only the Earth, to the best of my knowledge, has tectonic plates. So those plates are associated with the pieces of the lithosphere that actually float on the mantle. And so when we talk about continental drift, that is the essential reason why we're getting that continental drift, is because of the fact that the lithosphere and the continent, or the portion of crust that's on top of that lithosphere, is actually floating on the mantle, and it's moving backwards and forwards along the Earth along with its rotation. So the other thing I want to say is what causes geologic activity. The differentiation is one, and that's causing not just heavier stuff to fall to the bottom and lighter stuff to flow from the top. It also transmits heat. So when planets are very young, and we've talked about this, but I'm just going to put it in here for the sake of argument. There's accretion and differentiation. Accretion is like when the planet is actually collecting material. It has enough gravity that things are going to orbit it before it crashes into it. And differentiation, where the material is sinking to the bottom. Accretion is actually, by the way, responsible for a good portion of cratering events that happen on all the terrestrial planets. But the other thing that's happening that is current to the importance of a planetary's interior is the radioactive decay. So it is the radioactive decay which will actually make the planet interior hotter. Now, another thing I want to mention here is because of the fact that the core is a liquid and the mantle is a semi-liquid, what's it going to do? It's going, part of it that cools down is going to sink, just like cold air sinks and warm air rises. So the cooler stuff is going to sink, the warmer stuff is going to rise, but it's going to be in a cyclical form. And we call this cycle convection. So warm air comes up from the interior, cool air or cool stuff goes down in further deeper into the mantle, and thus it gets reheated. So it's actually a circulation, if you want to call it. If you want to call it anything, it's a circulation of hot and cold material. Now, the other thing that's happening with planetary interiors is what is called conduction. Now, just as a wire will conduct electricity, but a piece of plastic, if you stick a piece of plastic into an outlet, chances are you'll damage the outlet, but you will not get shocked. Whereas if you stick a piece of metal into the outlet, the chances are there's an emergency room trip in your future. Conduction also is responsible for transferring heat. So let's say, for the sake of argument, and I'll just pull numbers out of my hat. Maybe. There we go. Okay. So let's say that this is 100 degrees K. Just hear me out. 100 degrees K here. Okay, so there's 100 degrees. And out here, it's 10 degrees. And the question is there going to be a quantity called heat? And the answer is yes, of course. Okay, heat is dependent upon the change in temperature. So if I'm looking here at 100K, and then I'm looking here at 10K, where's the heat going to go? It's going to go from the high temperature to the low temperature. So it's going to go from 100 degrees K to 10 degrees K. So heat is going to radiate out. So this is a method of heat transfer. And then once you get to this surface here, the other method of transfer is called radiation, which basically uses waves to send the energy out into space. So this whole business here, and this is actually very important, the three processes: convection, transporting of hot materials to the surface, while cooler material circulates downward; conduction, the transfer of heat or electricity from one place to another. It's essentially transferring energy from one place to another. And then radiation, where the material will actually radiate out energy due to its radioactivity or due to its heat, etc. Question so far, we're okay? Question mark. Okay, now I bring up these three interiors, these types of problems, for one particular reason, and that is the question on the role of size. Size, sorry for the Dr. Ruth, but size means everything here, okay? Because the size determines how fast or how slow you cool down. So in the case of smaller worlds, what you're going to find is the interior cools off faster. Material starts out very, very hot at the core. So we're talking thousands of degrees. It gets convected up by circulation in the mantle to the surface. It gets conducted through the lithosphere to the surface and then radiated away by conduction. So this is the model that we have. And let me just show you what's going on here. The size of the planet, of the object, is going to make all the difference in the world because of the fact that larger size has more surface area and more volume, and therefore will transport heat slower in comparison to smaller planets. So if we're looking at one reason that these, maybe the interiors of the two giant worlds, Earth and Venus, are very hot, whereas the interiors of Mercury, Moon, and Mars are cold, it is size that is the big deal. Now, by size, we have to think about what is called the ratio of the surface area to the volume. Okay, now, once again, we have, and I'll try and draw this. I might be being very foolish, but I will try. Volume for a sphere, and we're assuming that all planets are spheres, is 4 pi okay, my pen's gonna work, really? Pi. Oh boy, okay. 4/3 pi r cubed is the volume of a sphere. The surface area of the sphere is equal to 4 pi r squared. So here is what's going on here. The ratio of surface area to volume is 4 pi r squared over 4/3 pi r cubed, and this results in a ratio of 3 to r, surface area to volume ratio. What does it mean? Larger bodies lose heat slower. Smaller bodies lose heat faster. It's like putting me out in 20-degree temperature and putting a baby out in 20-degree temperature. The question is, who has the greater surface area? And the answer is me. And so because I have a greater surface area, it's going to take longer for me to radiate out heat. Whereas with the baby, it just goes boom and it's gone. Okay, the upshot of this is that larger objects have smaller ratio, so a smaller ratio, and cool slower. Now that is the big deal, because when we talk about that, when we've said that, we can understand a little bit of what's going on with Mars, Mercury, and the Moon. These 3 planets are smaller, less surface area. Because they have less surface area, they radiate out heat faster. And because they radiate out heat faster, you actually wind up with a body that is colder sooner. Now, this has great effects on the ability of the planet to evolve geologically past getting bombed. And also it has import for the case of being able to protect its atmosphere. So the latter case is what is called a magnetic field. So not every planet, well, every planet has to some degree a magnetic field. Now, you've all seen magnets before. What is happening here is this magnet is being set up by the rotation and the rotation rate of the planet. So if the planet is rotating very, very fast, then you have more material that's being stirred up in the core. And because you have more material stirred up in the core, you actually wind up having a magnetic field. Now, I remind you, and you've probably seen this in 8th grade science or what have you, that magnetic fields point from north to south, and they actually circulate around the bar magnet. But this is also true in the case of a current going through a resistor, through wires. What you're going to see here is a magnetic field generated by this body because of the current that's being passed through. Okay. I'm sorry, folks. Can you give me about 5 minutes? Because I need to take care of something. Sorry.
Mhm.
Hello, folks. I'm so sorry. Uh, it's the joy of working from home, right?
Yeah.
Yeah. Okay. So I want to impress upon you the need of a magnetic field. So when we are looking at rotation, I'm sorry. Speak it right. Two ways that you can generate a magnetic field. One, you have to have a hot core. Number two, you have to have a decent rotation rate. So if you have a hot core, but your planet is rotating very slowly, you're not stirring things up enough to actually make a magnetic field. Okay, a magnetic field is made of current. Okay, you run charged particles in a circle, you generate a current, and that current in turn generates a magnetic field. If you're rotating at a decent rate, your core is also, I'm sorry, let me say it right. Your core is hot, and because it's hot, when you're rotating, that core is going to rotate too, but it's going to rotate at different rates. And because it is hot, electrons are going to get free and they're going to circulate around with the rotation rate. And when they do that, they generate a current. So when you have a current, you immediately have a magnetic field. Okay, so here is the upshot that I'm going to stick with. You have this inner core here that is circulating, and you have convection going on in the outer core, which is transporting hot objects downward and, I'm sorry, hot objects upward and cool objects downward. So when that circulation is happening this way, then what you're going to do is you're going to generate a current that goes like this. And because you have a current, you'll generate a magnetic field that goes through that loop of current and flows out much like this. Now, as we will see with Mars, Mars has a reasonable rotation rate, but its core is nearly dead. And because of that, the magnetic field is very, very weak. When you're out in space, just out in space, the environment can be very hostile. It's even more hostile around your parent star. So one of the things about the environment that is very hostile is the presence of what is called the solar wind. This is the radiation pressure that is pushing particles from the sun throughout the solar system. It's part of what has brushed away all the rubble during the age of formation. But also, it still goes on even after all the rubble is gone. But in this case, the charged particles and the other stuff that get involved in the solar ejecta, the solar wind will actually interact with these magnetic fields. They will actually curl around them instead of going through them. So if I have a good, strong magnetic field, I can protect myself against the solar wind. But if I don't, then I'm going to have some problems. And you'll see that on Mars. The other planet that will strike you as weird, and we'll have to talk about this, is Venus. Venus has a very hot core. However, it may be hot, but the rotation rate is so slow that there's hardly any circulation at all. This gives us magnetic fields for Venus that have been measured by the orbiters to be 10 to the minus 6 microteslas, so 10 to the minus 12 teslas. Very, very small magnetic field. Whereas with the Earth, there is a reasonably large magnetic field. It's not huge, but it's large enough that it protects our atmosphere. And then there's Mercury, which also has a weak magnetic field, surprisingly enough, but it's very, very weak. And because it is very, very weak, things get trapped near on the surface of Mercury. But it also might be that Mercury is indeed having some issues because of tidal locking with the sun. Okay, so with the whole business of a magnetic field, the three requirements are molten electrical conducting material, convection of that material, and moderately rapid rotation. Okay, so I want to make those points clear, that the interior is actually governing what's happening both atmospherically and with the with the atmosphere by the surface standards. The interior basically allows for the formation of the different types of volcanoes that we saw on the planet Zarquan, but it also gives rise to the ability to retain an atmosphere. And this is going to be a big deal. Okay, so questions? We're good?
I actually have a question.
Okay.
How likely, like, this could be a bit off topic, but I was watching a video of the other day about like Mars and like how it's possible for like colonization there. How how likely is it for us to like have a colony on Mars without the solar radiation affecting us? Because you were saying that the magnetic fields on Mars is pretty weak, right?
Yep. This is actually on topic.
Yeah.
And so part of the reason I brought this interior business up today is because of the fact that if you have a warm interior and you have a decent rotation rate, then you can actually get a magnetic field, which in turn will protect your atmosphere. One of the spacecraft that's actually exploring Mars right now and has been for the past like 5 years is a spacecraft called MAVEN, and it's the Mars Atmospheric Orbiter. And one of the first measurements it's made is, and I'll show you this in a little bit, is the fact that the Martian atmosphere is being blown away by the solar wind. Because it's a weak magnetic field, or a very weak magnetic field, the solar wind is actually able to to get closer down to the surface than it would otherwise. And because of that, there's a stripping of molecules from the atmosphere, which frankly will be tough to stop. I mean, if you're going to colonize Mars, you are going to be living in a habitat for the rest of your days. Any astronaut that goes to colonize Mars and stay on Mars is going to have to live in a habitat. There's just, at this stage, I would say the technology is not there to terraform the planet. The other thing that you need to keep in mind is the atmosphere is indeed carbon dioxide. We haven't talked about the atmosphere yet, and I'm going to, but I want to mention that because of that, because the atmosphere is thin, because there is not a lot of magnetic field, there's going to be a lot of hard radiation on the planet. Not nearly as much as Jupiter, as we will see, but enough that it would make it difficult, challenging to land on Mars and stay there. Okay, does that answer your question? Maybe not.
Yes.
Okay. enough to think about it. Now, science fiction is replete with examples of colonizing Mars and colonizing planets, objects in the solar system. Uh, the first couple that come to me are H.G. Wells's War of the Worlds, where Martians were actually invading the Earth. Another reference that I have that is rather interesting is Samuel L. Delaney's book Triton. There is a very interesting story because they're living on one of Neptune's moons that actually will more likely crash into its surface. I'm sorry, into its atmosphere. The third book that comes to my mind, at least immediately, is Ray Bradbury's Martian Chronicles. So if you are interested in that and seeing what the sci-fi writers write, those three books are definitely for you. But think about it. And so I'm not going to completely rule out the colonization of Mars. Would I colonize Venus? No, that's insane. But Mars has a chance because while its atmosphere is 95% carbon dioxide, it's still a little bit better behaved than something like a Venus where everything is carbon dioxide, runaway greenhouse effect. And that's another thing that you're going to have to figure out. If you're going to colonize Mars, you want a greenhouse effect. Now, let me just show you one thing. I'm jumping ahead of my game, but that's okay. Let's see if I can do this. Escape out, discard. Okay. This is a view. I don't know if you could, I think you can see this. This is a view of Mars and Earth side by side taken from the Solar System Explorer. This is what we think Mars looked like a few billion years ago. Okay, and this left side is what Mars looks like today. So this is Mars today. This was Mars at least 1 billion years ago. Or at least 2 billion years ago, excuse me.
We can't see. Are you casting something? Like, are you showing something?
Oh, yes, I am, and I'm evidently not showing it to you. Okay. Ah, okay. Can you see it now? Mars past and present?
Yeah.
Okay. So that's what I was talking about. I apologize. But you see Mars as it is today, and Mars as it could have been about 2+ billion years ago. What the heck happened to the water? This is really bizarre. And also, what happened to most of the air? And we think we understand that. We think we understand that. Okay, so let me go back to where I was. Okay. Okay, done. Okay. So I don't want that. Why am I doing that? Nope. Okay. So here's Mars past and present. Let me go ahead though and then discuss this with you. The name of the game though is not just atmosphere, but atmospheric retention. Okay, I am having no end of fun today. It feels like every bit of Monday. So now, just I'm going to take some looks at Mercury. I'm going to go through the geologic processes as best I can. I'm also going to give you some facts about Mercury, and also show you some images from Messenger, which is the current spacecraft in orbit around Mercury. So it's the innermost planet. It's locked in a 3-to-2 resonance with the sun, which means that it takes, for every 3 rotations, there's 2 revolutions. The second thing is that the surface of Mercury is highly cratered. This again suggests that the surface is very, very old. Okay, the more cratered you are, the more likely that you've aged quite a bit since your surface has actually reformed. And then third, the interior has a huge iron core and a weak magnetic field. There is a weak tectonic activity, and this comes not so much from the fact that the core is completely liquefied, but it is, at least we think it is. But more or less because heating and reheating has actually made the surface expand and contract. Okay. It's very, very difficult to observe Mercury with a telescope. It only gets to 28 degrees above the away from the sun at any elongation. So observing it with a telescope is very tough. The actual way that we were able to measure Mercury's rotation is via radar mapping. And we used radio telescopes here on Earth to send signals to and from Mercury. And by doing that, we've actually been able to discern this 3-to-2 ratio spin-orbit coupling. Okay. So let me get out of those and just show you the basic facts. Mercury data is 0.387 AU from the Earth or from the sun.
Are you showing us a slide show?
Oh, yes. Is it not showing up?
Or I don't see it.
Oh, boy. Okay. Hang on just a second. Okay. Can you see it now?
No.
No.
Mm-mm.
Okay, hang on just a second. Okay. So maybe that's the problem. All right. So let's see. Okay, can you see it now?
No.
I can see you, but no.
You can see me. Okay. Well, okay. Technical difficulties, always fun. Let's try and share this. How about now?
Yeah.
Okay, good enough. So just to kind of make some remarks, here's the data from Mercury. And what I did was I went on Solar System Explorer and I downloaded a shot of Mercury and Earth together in the same picture. And as you can see, there's a definite scale issue between them. So its eccentricity in orbit is 0.2206 and it drifts. So it doesn't just go, it doesn't just hit aphelion and perihelion. The actual aphelion actually rotates around the sun, and that's that spin orbit coupling business. Okay, so can you still see it? Is that okay?
Yeah. Oh.
Okay.
Yeah.
So this is what is called resonant rotation. The planet has actually gotten so locked up with the sun that and so stretched by the sun that it actually has a larger bump. So it's really, really elongated. And bottom line is that the planet will, its tidal bump will swing around and cause its perihelion to actually shift as it goes through. Okay, so here's the orbit, as you can see, starting with 1, as it goes around, it loses its speed, etc. So this shows the status of Mercury from the point of view of squashing, or what's the word for it? Oblateness. Mercury is one of the most oblate planets in the solar system. And what that has, the effect of that is that there is a rotation rate that deals with the oblateness, the stretching part, to actually face towards the sun. Okay, so as you can see, the orbit is not circular, but rather elliptical. And as a matter of fact, it's one of the largest elliptical orbits in the solar system as far as its eccentricity. Whoops, I wanted to show you this demo. So what you're seeing is the rotation rate being affected by this oblateness of the sphere. That's why this thing is taking so long. Okay, is there more? There should be more. Should be a lot more. Okay. Okay, so as this guy moves along in its orbit, it's getting stretched by the tidal forces of the sun. Now, as it moves to its aphelion, the bump does not stay as close to the sun as otherwise. Okay, so missions to Mercury, there haven't been a lot, but the ones that are noted are Mariner 10, which was in 1974. It flew by Venus and then it flew by Mercury. It took some nice shots and revealed a terrain that is very close to being like the moon, except its resolution wasn't so good. It was later with Messenger that we actually got very good surface feature resolution. So again, if Trisha's flying by, what she sees is that it looks kind of similar to the moon. If we look at, for example, the splash marks on the craters, the basins plus extra craters here. Okay, again, this is the light side, this is the dark side. The light side is going to be about 700 and something, I'm sorry, 683K, and the nighttime side is going to be about 100K. So from a global perspective, we again have craters within craters, and again, I put the comparison of the moon and Mercury together so that you can see the differences in their geological features. Now, once again, you're looking at a pretty much a dead world because you have lots and lots of craters, and you have lots and lots of craters within craters, smaller and larger ones. You also have a little bit of what is called Maria. You have more of that on the Earth's moon here and here and Here would also be a good idea. Okay, so another thing is that Mercury is a volatile rich planet. So by volatiles, I mean materials that can evaporate very quickly, but are very, very useful for planet building and so on and so forth. All right, and I apologize. I need to take one more intermission. I, again, am so sorry. Hang on for just a minute, please. I apologize again. Sorry, folks. Everybody okay?
Yeah.
Yes.
Okay. Yeah, we're having that much fun too. Okay, let me share a little something with you. And I'll try to get this right. There it is. You can see volatiles, is that correct? Nope, you're seeing the other side. Let me flip the screen. There we go. So this is a volatile-rich planet, and let me just play this for you. That's why this thing is half a meg or half a gig. So here is the sizes of the planets, and you can see there's a large amount of potassium and thorium in Mercury in comparison to the Earth, and the other one is a potassium-thorium ratio. Mars is another planet that is very heavy in potassium and sulfur. Now, I don't know if you guys have ever done this. I would recommend you don't, is putting potassium in water. It's a very bad idea. Don't do it at home by any means, and do it under professional supervision, because potassium has a tendency to explode when it gets into water. However, those are very valuable minerals that we could use. So as far as mercury goes, is it a living rock? Probably not. Is it something that you could live on? Potentially at the Terminator. And potentially, I don't know. There was a book called Rendezvous with Rama, written by Arthur C. Clarke, and he actually put a colony on Mercury at the Terminator, where the temperatures are actually reasonable. Temperatures on the day side are 683 K, so you definitely melt a few things if you tried to live there. And then the night side is minus 100. So you definitely freeze anything that you need, that you would want to be there for. And so Terminator would probably be the best alternative, meaning the separation between light and dark. So this is a volatile-rich planet. So just to look at geology a tiny bit more. So this is a mosaic of the different faces of Mercury as taken from the Messenger spacecraft. And what I want to point out to you is like things like, well, let me get a pen. There we go. Again, you're looking at splash marks that are very similar to those on the moon here and here and here. You have lunar highlands and cratered areas that are very similar to the moon. And once again, the crater within crater within crater. That's what's happening here. You can see, and you actually probably could do this now. You could actually start measuring these craters by figuring out this picture. This scale is 50 kilometers. So if you were to hold your ruler up to it, like if I hold my ruler up to the screen, which may not be the best example, but that's the best I can do at the moment. Whoops. Then I would get 50 kilometers divided by 1.5 centimeters. So 50 km divided by 3/2 centimeters will give me, let's see, 2 times 50, 100 divided by 3. So it's 33.3 kilometers per centimeter. And then I could actually go ahead and measure those craters and figure out what their sizes are. But again, I want you to notice the craters within craters within craters. And this tells you that there is not a lot of geologic activity. However, if we look at this area here and some of these other areas like this one up here, and there's more, but I'll have to see if I can dig them up, then what you may note with these areas here is that the mercury is actually stretching and contracting, and this comes from the uneven heating between the day and the night side. So what you have is tectonic activity because of thermal heating, because it's so close to the sun. Parts of it that are exposed to the sun are getting stretched. Other parts that are away from the sun are contracting. So you have that whole scrunching, uneven scrunching between the two. So here's another shot of it. Heavy cratered smooth regions. The smooth regions are actually lava flows, and that would probably be true. And then again, you have these escarpments right here, for example. There is a crater, basically these, if you go up here, I can't see what's there. But once again, looking at some of this, could be lava flow. Some of this, though, could be stretching and contracting. Because if you're going to, if you take a surface and the sorry, the crust is very low density, but it's very malleable. And what you can do is by heating it up, you're stretching, just like you would stretch Play-Doh, or just like you would stretch silly putty. We had a lab that we were going to do with silly putty. Sad. But here's the thing. Yes, you can stretch, but try stretching, putting Play-Doh or silly putty in a Ziploc bag and sticking it in warm water for a few minutes, and then try and stretch it. Or put it in the ice box for a few minutes and then try and stretch it or push it together. And you'll actually see this whole problem of uneven heating and what that does to a malleable surface. So that's what's going on here. So here's another shot. This is the Rembrandt Basin. And again, this is a basin is formed when one of the meteors actually cracks the crust, allowing the mantle to fill in. So now you have basically in here, in this region, you have a setup of a lava plain. And then you'll notice that that lava plain has also been hit many more times by different falling bodies. And again, the craters are not very large. You have a scale. You could literally just go ahead and do the scale run. I know this lab was probably not the easiest lab you've ever done, but I hope that it also gave you that sense of scale, that maybe it makes more sense on how we do these things and how we figure out the size of these things. So anyway, last but not least, let me show you one other thing. The core and mantle shrink and the core and mantle expand. So that's why we see these little escarpments going through the craters. And again, that's a thermal expansion and contraction that's going on as Mercury orbits the sun. So I threw some further images out here, and I'm not going to do a lot with them, except these give you some idea of what this planet looks like. This is in false color, and what they tried to do with it is they were illustrating lowlands are actually darker and highlands are actually lighter. So you can actually tell depth based on the color that you see here. And you're actually looking at a plane that probably formed up due to, again, thermal expansion. And then as the plane expanded, it also got hit by different meteoroids or comet or things of that nature. Now, as a matter of fact, it did get hit by comets, and because of that, there is actually polar water deposits, which is kind of odd. Let me just let this guy go. Yeah, there we go. Okay, so this is above the polar, the North Pole of Mercury, and you can actually notice that it is not as heavily cratered. The blue again is lowlands, the red is higher lands, but again, you have all these craters here, not as many, but the other thing you can see in the center here is water deposits, and they actually detected that through spectroscopy. Okay, this is actually from the Messenger spacecraft as it's orbiting around. Okay, let me just go on. Here again, some planes taken again by Messenger. This is if you look at this, it is a bit smooth. It's very similar to what you see on the moon. And as a matter of fact, it is the same issue that happened on the moon. What you see here is lava flow from a very large impact. And that lava flow actually filled in this basin. And then you'll notice that this basin has been filled in, has been hit with rocks or hit with meteors, but also notice the crinkling effect. And again, this comes down to thermal expansion, contraction, expansion, contraction. Some more detailed images. These are from spectral. They're basically spectral analyzed, and what you see here is a water deposit on the surface of Mercury. So here again is water deposits, and that's an interesting point. You would think, hey, there's not. Why in the world would there be water on Mercury? The answer is there's water everywhere. They found water on the moon. The only place that I can tell you right now does not have water is Venus. And as a side note, I am going to be making a recording on Venus and Earth tonight. So that's going to be something that'll show up here in the Teams shell, and maybe on D2L as well. But anyway, let's see. Where are we at? Okay, so this is a shot of the Hakusai crater. Currently, one spacecraft is orbiting Mercury right now. Messenger is actually gone. That mission ended about 3 or 4 years ago. But the Japanese are actually have a spacecraft that is orbiting Mercury right now. And this one is actually taken. This one actually was from Messenger, but it was named after a Japanese discoverer. This is a shot from Mariner 10, and actually this is a video. Let me show you this. Okay, my apologies. Things have not done as they seem. So here we are. So this is a flyby using the technology of Mariner 10. Notice that there's a huge difference between what you see from Mariner and what you see from Messenger. So this is the resolution given by messenger versus the that when it flew over that same region. Compare that to what you see with Mercury with the Mariner 10 flyby. Okay, so one other thing is that the surface gravity of Mercury is about 3.73 meters per second squared. So if we look at the moon, hitting the moon and hitting Mercury, because the moon's gravity is half of what Mercury's gravity is, the ejecta from the craters will actually travel a lot farther on the moon than it will on Mercury, and that's again because of the gravity. So, core and atmosphere. To say a few words on that. I know we're low on time, but let me say what I can. There is an offset magnetic field, and here's what's weird about that. Again, I said that the core of Mercury takes about 75% of the radius. So if I look at this now, the magnetic field, what is it doing on the planet? Let's find out. So here again is Mercury being bombarded by the solar wind, and there's actually a shield. It's shielding the planet from some of the harder radiation. Notice how that shield is actually being blown to the side, and notice the distortion that is coming from the fact that the wind is so strong at this region. So once again, the possibility of living on Mercury is a little dubious because of the fact that it has it does have a magnetic field which will deflect some of the sun's harmful radiation, but not all. Okay, now there are duplicate slides here, which is probably why things are goofy. So here's the dynamic magnetosphere of Mercury. I like the video demonstration better than trying to draw it out or things like that. But notice again, this is the escaping material is gases that are escaping off of Mercury's surface because of the solar wind. So while the solar wind does protect, to some degree, it also it does do some damage too. Okay, so here is a comparison of the moon's core to the core of Mercury. Once again, we have the mantle here in gray. The core is here. The lithosphere and crust is at this part, the purple part. And again, the big deal here is the fact that Mercury's core is to some degree hot. Okay, we think that this is tidal effects of the sun, because the sun is actually stretching Mercury out and making it stretch and contract and stretch and contract. And every time it does that, it actually adds heat to the interior. And by adding heat to the interior, you're actually able to keep the core warm. We have not checked the radiation of the rocks, and we actually haven't landed anything on Mercury, so we don't know. Whereas if you look at the moon, yes, it's getting stretched and contracted by the Earth, but the gravitational strength is not nearly as strong as comparison. So if we look now at the core of the moon, we can see that the core of the moon is dead. And therefore, we're not going to see a lot of activity on the moon in comparison to Mercury. Here's another comparison of Earth and Mercury as far as cores go, notice that there's a solid inner core here, liquid middle core at this point, and a mantle that is far smaller than the mantle of the Earth. Okay, and again, the relative size to show you the size of things. Now, the last thing I'm going to say, and then I'm going to stop, is actually question: how in the world did Mercury actually get such a huge core? The answer we think is a collision with a large body during formation. So as the collider smashed into Mercury, what probably happened is most of Mercury's mantle was blown off, and when the planet reformed, it actually reformed with just a crustal area, a liquid crust at that point, and a huge iron core. So if we look at proto-Mercury, here is the possibility of it getting hit by a planetesimal that's about 1/6 the mass of proto-Mercury. And again, there's a stretch of about 5,000 kilometers. The planetesimal blows into proto-Mercury interior, blasting off all the material, the mantle material. And so when, as it vaporizes, the other parts reform, but the mantle is gone, and so we're left with a core. So there's very little atmosphere. There's basically some hydrogen and helium captured from the solar wind, atoms of neon and calcium knocked out by rocks, by energetic solar wind particles. It lost its primordial atmosphere billions of years ago because it's too close, frankly, it's too close to the sun. But Mercury is going to be very much like Mars, very much like Venus, very much like the Earth. It will have as its secondary atmosphere, and we'll talk more about this on Wednesday because I really want to get into the whole atmospheric dynamics thing. But what has happened here is all 4 of the terrestrial planets will be shown, fossil record, etc., that they initially had very rich, dense carbon dioxide, nitrogen atmosphere. The carbon dioxide, nitrogen atmosphere will start there for all of these planets. But the evolution of that atmosphere is going to depend, again, upon the geologic activity and the core of the planet. Okay, so I know I did not get to Mars, and I know I did not get to the moon. What I may have to do is I might have to tape those as well, or we might have, if we get a chance, we'll discuss them on Wednesday. In the meantime, I do believe that, let me get out of this and let me get back into Teams. Okay, and hopefully I didn't scare too many of you away. This was not one of my better days, unfortunately. Let's see. So this is my presentation. Hang on, let me share this. And screen 1. Here we go. Okay, so let's see. Yeah, really, come on. All right, so in Teams, in the lecture notes, I have just posted up the presentation of today, which also has Mars and the moon. I will focus any Quizlet that I do for that's going to show up either tonight or tomorrow on the interior of the planet and on Mercury, on any of the facts that are going on with Mercury. Any questions, all?
When is the lab due?
The lab was the cratering lab was actually due. Let's double check that, unless somebody else knows.
I think it's due today at like
It
11.
is due today. Yes,
Yeah.
that's right.
No, I was asking about the climate lab.
Oh, the climate lab. Well, I think what we're going to do with the climate lab is I'm going to talk about climate on Wednesday, and then you'll have that lab over the weekend. Is that more reasonable?
Yeah, that is.
Okay. All right. Except Patricia, she has to do it tomorrow, and we compare answers. No, just kidding. Anyway.
All right, Ubi.
How are things going at CCA, by the way?
I mean, honestly, this is just really hard. I mean, I got a house full of kids right now, and I heard a baby in the background for you. So everything is pretty much, I guess, really hard for everyone trying to figure out how to make a desk in, a classroom at home.
Yep, I know that feeling. Yeah, I have one. She is opening doors and coming into places she shouldn't come into, and I'm trying to keep her out of my lab because I've got a lot of electronics going, and she would get hurt here.
Oh yeah, so, they nosy. They nosy.
They're very nosy, And we have another one coming along in August. Lucky her. So take two, they're small. Anyway, we're all doing the best we can, and I will do the best I can on things. I've noticed again, people are still not able to see their damn grades, and that's frustrating me right now because I don't know what else to do with the darn thing. But I might have to contact tech support at some point in time today and see if they can't get me so that I can show you your grades. Because I'm sure you would all like to know. But I'll be honest with you, what I saw of the grade book is I don't think anybody's getting lower than a B. So don't do anything silly, okay?
Okay.
Yeah,
okay.
We'll get you through this. Okay?
All right.
All right, folks, you have yourselves a good day. Watch for another meeting. Is it helpful that I'm doing the meetings in class during regular class time, or would you rather them differently?
Honestly, to each